Welcome everyone, how's it going? Welcome to another stream, hope you're all doing good. So, just that we're live, we're in a good place, there we go. So, yeah, last stream was looking at like the game side representation of the map and how we might share that with the renderer, because I was thinking of like effectively some other future problems to try and see if we can just get it all done in one kind of go here. We want to render a scene, and in the future we want to render like a top-down map kind of thing, and probably global illumination. So I was thinking maybe it's better if the renderer just has the map, then it can go and just do a whole bunch of stuff with the whole map information. And so we finished the stream sort of probably going down that approach. So that was option number 2, basically. But I'm not sure if it's where I want to be going, though. Let me just git diff this. Yeah, we didn't particularly do too much. We've made some good changes, though. Oh yeah, we've made it the palette, material palette, a concept in the graphics API. So now you can send material palettes from the game side to the renderer, the ones which you'll be using this frame, which is cool. So I think I might want to do a bit more thinking on today, just to make sure we're going down the right way, because we could go and implement something and then think, you know what, maybe it's, we just put a little bit more effort into thinking, we could have saved writing a whole bunch of code, basically. So yeah, I've got some more ideas, basically, I want to play around with. But yeah, any questions, feel free to ask away. Let's start off with a prayer, then we'll get going. Father in heaven, we thank you, Lord, for this day. We bless your holy name. Thank you, Lord, for being our great provider. We thank you, Lord, for all the things you do in our lives that we see and do not see. Lord, we just pray for your mercy, your forgiveness. All those times we've strayed from the path, all those times that we've sinned, all those times we've not followed your way. Please show us mercy and forgiveness, Lord, and help us align to your will. Help us be better inside and out. And help lead us into paths of righteousness for your name's sake. Thank you, Lord. Father, I just pray that each and every one of our viewers gets to know you. Keep knocking on their door. Keep sending those people in their lives. Keep putting those videos in their feeds. Keep doing the good work that you're doing in their lives, Lord God. Lord, I pray you keep softening their hearts and showing them that, your time is coming soon. I just pray for them to be woken up in the mighty name of Jesus. And also pray, Lord, that you help us. Help me, Lord, give me the spirit of wisdom, of understanding, of counsel, of might, of fear of the Lord. Help me understand how I should structure this thing that I'm working on today, and help it be a minimal thing that I can implement, solves as many problems as it solves all the problems I need in the present and coming future well. And help me come to that conclusion quickly. Thank you, Lord. In Jesus' name we pray. Amen. Cool. Right. Beautiful. So today we're trying to have a bit of a think. So one thing is in the current system that we have is we go to the graphics, and we kind of made these voxel models to be things that you can import from Magica Voxel, right? And they go up to 256 or 255 cubed, right? It's kind of interesting. You know, our chunks are 16 by 16. So that's another thing. But the other limitation they have is the materials. The material limitation that they have is only up to 16 different materials. Okay. So the problem that we've been bumping into is we want to render, or is it logic render? We basically want to try and render a map, right? And we've got this sort of like payload that we're filling up from the game logic side to say, right, render all this stuff for me. But we're kind of like breaking down each of these. I can't even show it anymore, can I? Yeah, we're breaking down all of the. Can I run it? That would be. Maybe I can. Uh, Chunk update. Okay, let's leave that commented out for now. There we go. Okay, so it's rendering now. So this is just a map, and each one of these blocks here is come on, is an instance, and it's doing 16 by 16 voxels in there, right? And we do some occlusion culling on those, so it allows us to draw. Yeah, so the great thing about this is they're just little triangles like this. They're a reasonable size, I guess. Or maybe not because the orientation of them. But well, yeah, if the thing's bigger, then yeah, they would be. Depends on resolution, but yeah. So the great thing about this is what the occlusion culling. So we won't render the ones which go behind, but they're still sent to the GPU in that fashion. You know, I was thinking like, say one of the things is that we're going to be doing is, say we wanted to turn this into like a thing to use for GI. You would kind of want the whole voxel map available in a way. So you could like ray trace through it basically. And you will want the renderer to have all of that voxel map so it can make that sort of octree data structure. But I'm wondering, if, yeah, so the other problem is like you're sending into this payload a lot of a lot of model instances, right? So we could say around the camera, let's grab so many chunks worth around the camera and then send all of those. But then that would be, say if you had, how many is on the screen? Do you see? As you see like 4, 8, 12. So there's maybe 24. So you're seeing like 48 on the screen, right? So let's just round up to the nearest power of 2. So 64 by 64. It's like 4,000 of them. But there might be more than that. Might be a few layers of these things going on and stuff like that. So you could probably quite easily times it by another, let's say 24. That's already nearly 100,000 instances that you're sending from the, and that's just the map alone. Quite possibly, you might have little entities as well. So another way we could structure this was that we would say the whole render thread gets its own copy of the map, and it will basically make the voxel model instances from that. And it still has the same problem though. Effectively, it doesn't really solve this issue too well. It's just it won't be sending it via a payload system. Instead, it will be sending the map updates, the chunk updates. So I was thinking though, what is interesting is we already kind of have this problem in a way, where the game wants to generate some kind of voxel data that the renderer uses. And that is when it comes to the generate, you can generate a voxel model basically. So perhaps maybe our voxel models are too granular and we should be doing them as chunks. Maybe. But each model is already a little voxel model of 16 by 16. That's maybe a bit too small. I'm not sure. We might be thinking, yeah. Because you can sort of make them out there at 4K, so maybe they're fine. They're super small though. But so if we had a chunk which is, so yeah, a chunk is 16 by 16, isn't it? 16 cube, which is 2, right. So if each of those, yes, each one of these blocks already has 4,096 voxels. Yeah, so it's like it's 256 cube basically, which is probably for, well, 16 million. So maybe that chunk would be far too big. I was thinking maybe we could take 16 by 16 of these like blocks and just put them into one big model and just send that over. We're already kind of doing that. Yeah, so maybe our chunks could be bigger. So 64, 64, 64. So that would be just 4 voxels though, wouldn't it? Sorry, not 4 voxels, 4 of these blocks. If you used to take those like cubed 4x4x4 and sent those, and that could be a thing that you render. Then we run into material palettes not being big enough. Right, stuff to think about. I'll be right back, just gonna get a drink. It's getting warm now already. Right, welcome back. Man, it's very hot now. Okay. So potentially this, the level that we've broken down these instances is fine. They should be these 1x1 blocks. Because how dense the voxels are already. Okay. So could we introduce another concept? I guess what this what the voxel map is. It's like a grid aligned. Yeah, I guess that's what we're already kind of doing, right? We're kind of saying, so this whole sort of voxel chunk and map thing is basically saying I want a bunch of grid aligned model instances which aren't necessarily going to be the same things. Yeah, I think that's what it is. Okay. Yeah, I think this is the right approach then. So if you give the game this map, and this map can be updated. And I think there can only be one of these maps at one time. But yeah, potentially this is the right thing to be doing then. So I don't have to keep uploading that in the payload. Right, let's get this thing in the... So this just will index a chunk. I think there's a way to do... Yeah, I think it's completely fine. They're 16 by 16 by 16, so it should be alright just to do the classical, like, oh, map chunks coord dot z. I got a thing called like flatten here, haven't I? Flatten 3D. Map width. See, why isn't the map got its own dims? Why has it got to be doing it that sort of silly way? Lovely. Then take the address, obviously. Okay. So where was we? So let's just go from the game side then and generate a very let's generate a map. The thing is about these chunks is it's always going to take space up, isn't it? When you could have chunks which are like inactive and stuff like that. Like if you didn't want it all loaded. Yeah, if you didn't want it all loaded, you'll basically have it. Yeah, we're going to have it always loaded. Right, let's do that. We can always have unloaded chunks. Okay, so let's go to the game side of things and let's find where the map gets initialized. So we've got this sort of like game world map and it's this sort of map here. So we probably want some kind of initialization function or something like that. You know, this is part of the payload. Maybe the map can just be in a separate section. Because it seems like it's going to want its own things. The Voxel update, though, that is different. Do, 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 do. Yeah, so here we can like initialize it and all that, right? We can do a good old init. So you pass in your allocator, I guess. Well, it doesn't really need one. You could just pass in how big you want it though. Nice. We might have some more things in the future, but this will do for now. So I guess you can make it like dynamically do different chunk sizes and stuff, but we don't want that for this, but we can always just change the layer right if need be. So map dims equal dims, right? And map chunks equals allocate me an array, please, with type graphics rendered chunk the allocator is going to be the static allocator, and this would be product elements of dims, yeah, and voila. Cool. So we've got that lovely thing there. So inside the game, when we instantiate the world, which I don't know where that is, here. So wmap, and the dimensions. This is the fun thing about it. Gonna be big. Gonna be quite big, isn't it? So 1024 by 64 by 1024. This is the current plan. So we are also going to get, this should all be zeroed, right? So all of those values should be basically empty slots. Now, at this point, so you'd have a section which would do like generation and all of that, right? Now, we need to like, what do we need to do? We need to, yeah, we need to set some data at some point, and then we need to say like, send the whole map to the renderer basically. So there should be a, so there's a sort of map chunk updates, it's a queue. So we did like 1024 divided by, well, it's 1024 times 1024 times by 64. That's how many chunks there is. It's quite a bit. So you want to eventually send all those updates to the renderer. That's so many chunks. Sorry, that's not how many chunks there are. I got that completely wrong. It's divided by 16. Right, 64. And yeah, we need 64 as well. What's that divided by 16? 4. Okay, so 64 by 64 by 4. That's how many chunks there are, right? 16k chunks, which is a power of 2. So it's quite handy. So we could set up yeah, so you could do these map chunk updates. So I think for the initial state, maybe the payload or whatever, the logic thread could send the render thread. It could literally send just a pointer to the data maybe, and then it will read that. No, because then you'll get some read write. No, because then you can just say it doesn't get simulated anymore until it's read it. Yeah, so you could maybe guarantee that the game logic never like modifies its value again. Right, its map state. It never modifies that. Just sends a pointer to it, and then the renderer just takes a complete copy. Then from then on out, you're just doing little updates if they change. And that should be a lot more efficient, right? Yeah, so let's do like a little generate thing here. If I'm wondering, so say if you like say, hey, regenerate the map, right? Potentially, all right, here's what you could do. You could say to the renderer, right, we're going to trigger a reload, loading a new map now, and here's the data for it. So you've just like, you've in the background been like generating a new map. You've got a new pointer now, and you want to wait for the renderer to take it and say it's got a copy of it, and then yeah, I wonder if it's just going to stay static. To be honest. Yeah, the whole thing would be a lot easier if we didn't need to mutate it. I don't think there's going to be cases where we mutate the map, is there? No, I think there will be cases where we mutate the map. Yeah, let's just put it in. So the game could generate a map and then tell the renderer somehow, like, hey, can we reload this map? And that should be probably outside of the payload API or whatever. And maybe you have like a map hash or something like this that you're saying, hey, we're using this map, this frame. So it can load the new one in the background. And then when the new one's loaded, it can sort of swap over to it and then basically get rid of the other one when all of the, after a few frames have been rendered. Something like that. And that should be efficient enough. Yeah, then we won't have to have very big update queues and things like this. I wonder if for the queues we don't have, I don't have like a little queue abstraction other than the multi-consumer one. Hmm. If you roll it back. So I'm thinking about like, if we're doing this payload thing and we do any rollback System maybe. Well, the persistent state on the renderer. If you're getting these updates, these chunk updates, yeah, it's going to have issues, isn't it? Yeah, so maybe a better approach then is chunk hashes, and there'll be a chunk storage somewhere. Yeah, this might be the better idea. So we calculate, right, that there's 64 by 64 chunks, which is, because 64 times 16 is 1024, right? Okay, so 64 by 4, there's only 16,000 chunks. So if you literally send the whole renderer a bunch of chunk hashes, and a chunk hash is maybe 8 bytes, that's a lot more manageable. But you know, don't not even sending a hash, you're sending like a chunk pointer. Yeah, just send a chunk pointer. Right, send a chunk pointer. And yeah, this is way better idea. This is a way better idea. Okay. So you get rid of this stupid queue, right? I don't need to build a queue abstraction. This is great. It was an interesting idea, but it doesn't make sense. A better idea is you want to have this sort of map is a bunch of chunk pointers. And you want to be sending every frame a list of chunk pointers. And the idea is these chunk pointers will be buffered up to a few frames. So if you change a chunk, that chunk will be sort of copy on write. And it would then, that old copy would live for a few frames, such that if you did any rollback system because of networking or whatever, then that chunk data would not be destroyed if it was to roll back, right? And that is the way we should do it. So every single so we just send the full quote unquote map, but it's really just pointers to different chunks. So what we need is like the game side is a sort of like a chunk allocator or whatever you want to call it, chunk buffer. And that will do it. I'm not sure why this is in a header file and other things are not. It's all really kind of dumb. We should move it all to the header file, to be honest, and sort that out. But right, this is the way to go. We've found it. It's amazing. All right, I'm gonna take a quick break. It's too warm in this room. I'm gonna cool it down a bit, BRB. Right. Let's get started with this idea. This is going to be awesome. Man. So I think let's move some stuff to the header file. I don't know. Can I like B-split this? Yeah, but I want to like open up the game or something like that, innit? Game C. That's the one. Right, so where's my lovely little headers that I usually do? These guys. Wait, where are you? Right, so let's just say this is like entity or whatever. Entity stuff, which we'll do when we are done with the map. Let's just say this is like the world. Right, let's bring that back to the... This is like debug drawing stuff on the game thread. Now, we also have this game thing. I'm not sure what the difference is between the game and the like... Do 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 do. I'm not sure what the difference is with this. Right, so let's look at these sort of game materials. Like what goes in the world and what goes in the game, basically. Like, I think the world is meant to be this isolated thing, which you can have many different world instances and whatever. Yeah, I think. Yeah, and it's. You're meant to be able to basically start a new world. Like, a new frame would be a new world, I think, is the idea. And you copy all the data over. I was thinking about maybe going with that approach. And persistent state stays in the game. Something like that. I think that was the plan. But yeah, let's move this over here as well. I think I'm having a fixed time step as well because just because for reasons. Now I was thinking about also having let's plop that in there. Job done. What's this build queue thingy? Build queue thingy is because that's the build systems. The build systems can say, hey game, this stuff is done building. What do you want to do about it? And the game's like, I'll reload it. Of course. Game. There we go. Okay, so we're getting closer. Now, so we'll put some more like things in here, sections for like the chunk system and all that, which we'll be building. So let's just do a debug draw section. Let's go and find all those debug draw thingies. We'll put them at the top of the file. So entity stuff can go here. Then the world related stuff, game world. Then the material. Then the game stuff at the end. So this is material bits, game material, cache, and all that lovely. Those should really be declared in the header file. So I like having the header files so we can see what's in the C file rather than having to like sift through it. We can we can just view the data and what the functions are, but not the contents of the functions and all that. And see. Right, so this is looking kind of gamey to me. Game render. Right, we'll bring all these logic render tick camera set. This is to the input. And this is the material stuff. Beautiful. Okay. Let's grab this material stuff. So this one's like a G game thingy. There we go. So when it comes to the material section, got these sorts of functions in it. Let's get them in there. Oh. And we'll see. And there's a, oh, that's an interesting one. There's a sort, and then a UI. So that's the material palette UI that we made before we started the game streams, which is cool. It's nice and clean now. And let's put this in here. And they might get reordered at some point, but let's just get them at least defined ahead of time so we can keep track of what's in here. Game camera set. That seems like a game world thing. We'll sort that out some other time. We just want to get some idea of what's in here. Game render. Game logic thread. Runs on a separate thread. There's a before. DLL reload after DLL reload. So it basically reinstantiates all the global variables and yeah, it just reinstantiates all the global variables. Oh, and sorts out any function pointers. Like in hash tables, they're function pointers. So we just repatch those in with the new ones, basically. It's a bit annoying, but the idea is don't use many hash tables, right? Just use the ones that you need. Shouldn't be too many. So now, handler does a lot. And there we go. Right, okay, cool. Just get these in here. So, we can clean them up a bit better later on. But now we've got some kind of order amongst the chaos. We can add more order later. So the idea was, pretty cool idea. So this game world, right, we want to make it kind of have like a copy of every frame, but copying a whole voxel map every frame will kind of be crazy, right? And same thing is from the game logic thread, we want to send the render thread the whole map, but copying the whole map every frame and filling up a payload with that is kind of crazy, right? Like 1024 by 1024 by 64 is like 68 megabytes, quite a lot. So what if we, instead of sending the map data itself, we sent the map, but we sent pointers to chunks rather than actual chunk data as a whole, right? That would kind of be interesting, right? So that would mean then we would need to like buffer the, so if you were to change a chunk, it's copy on write, and the old chunk will live as many frames as there are rollback, right? For when we do networking, basically, then we'll be able to roll back to a previous state of the world, and the system can still point to that data, right? But it just recycles it later. So what we would want is like a chunk allocator or something like that. So when you have a chunk in the world, you want to be able to like you want to say like, hey, clone this, but when you clone it, you are basically saying to the other one, bye bye, right? You're putting it on a countdown until it gets recycled. So we could probably it's just a pool allocator basically, but with some extra stuff, right? What can I say? See, prefixing everything with the name game might be a bit annoying, but let's just do it. Game chunk pool or something like that. So the idea is you have probably an object pool. Yeah, so the issue is you cannot tell whether this thing is so if you use the object the best thing about the object pool is you're now using like IDs instead of pointers. You can check use half to freeze and all of that, right? So maybe instead we can put the redundant we can build a different system where we put the redundancy inside. Yeah. The thing is though, is the game yeah, it's not really thread safe either if we use the object pool. But yeah, so we've got a complete manual system. That's completely fine. No biggies with that. So graphics render chunk. Right, so here's just all your chunks. Now, the thing you want to yeah, but why is the game doing all of this? Why isn't just the graphics system doing it? Yeah, so maybe you can have like a map. Right, I got some ideas. Maybe you can have so in the graphics system you have like let's get rid of this then. Maybe you call it like map storage. I don't know what you want to call it, but let's just call it map storage for now. Let's just kind of scope the idea of this thing out. So it's like you just have a bunch of chunks, right? And each chunk. So the great thing about this is it's just a bunch of U16s. And so that'll be, it's 16 by 16 by 16, which gives you 4K, but and then it's times 2 bytes, so it's 8K, right? There's 8K of information per chunk. Now, I was thinking if you have a pointer in one of these maps to that, how do you know if that chunk hasn't been sort of like recycled, right? So it's been freed, or sorry, it's been copied it's been copied, and then it's going to be given a few frames to tick over, and then boom, it has been completely it's completely gone now. So usually you'll tick like an integer somewhere, like a counter, to sort of know like this is a new generation now. It's a new, completely different chunk. And if you just use pointers, you can't really do that. You've got the high bits, right? You can probably put some extra things in there. We could actually, though, encode some stuff in the low bits, because they're literally 8K, right, in size. So if they're 8K in size, right, that's a big number, right? The you know the There you go. Look how many bits that is at the bottom. Ba-ba-da-dun-dun-dun. So we could store the count thing at the bottom. Oh, this is incredible. This is so good. So you can store the you'll call it a type def chunk star. You'll call it a no. It's got to be you can call it a chunk reference. And we'll just do U64. It's a raw thing. Okay. So how do you go from a chunk ref to a pointer? We just end out the low bits, and voila. Man, that's gonna be so good. So you want to do graphics render chunk. Sorry, voxel chunk ref pointer. And you also want to be able to get the generation. And there's a certain number of bits in there for the generation. You could really just do some things here. So because it's 16 by 16, and then you could do chunk ref generation mask. What was that again? So it was, that's right, isn't it? So it's 16 by 16 by 16 times by 2. Yeah, okay, good. So if you knot those bits there, bitwise not, and you alright, it's 1 FFF, isn't it? That's it. Yeah, okay, so lovely. And that's how you get rid of the generation as well. So if you want to make a reference, render voxel chunk ref, you're taking a pointer and you're taking a generation. Now, ideally, we should ensure that that pointer is like aligned and everything like that. But I guess you'll find out if it's not. But yeah, so you do something like pointer. Yeah, you'll find out quite soon if it's not. pointer turned into U64 basically, or with a generation. And then if your generation overflows the mask, again, you'll find out pretty soon. Right, literally right away, you'll find a problem. So I think I'm happy with that. So then how would you get a pointer from a reference? Well, it's simply chunk pointer how's it going, Brian? Walk sun coding in the terminal. It's like the AEs. Yeah. You know, why not? Performance is good. You know, you get the modal text editing. You're not running a web browser, just a program. Good times. What text editor do you use by any chance? Man, this is so good. Such a great idea. Literally just what we prayed for at the start of the stream. Prayed for good ideas. Good ideas came. So ref pointer, and then I guess you can get the generation as well. I usually call them counters though. Do I call them counters? I don't know. No, I call it generation in this code base. Right, good. So, generation would be, oh wait, that's a not. Yeah, the pointer needs a not, and then the generation wants. To be so good. So good. So we're now considering this thing called like, there we go, we've got some lovely, you know, screaming macros now. Much better than functions. Now, we're considering like a map storage, right? So you have a bunch of chunks and you probably want to have their generation stored. Yes, you probably have like a chunks capacity, right? It's a capacity for the number of chunks. And you want to have like probably those generation counters. So we saw we had how many bits? There was 12, 4, 8, 12, 13 bits, right? So U16 generations. So I reckon this map storage wants to be accessible from basically everywhere. So I guess the graphics system just has this. And it will manage it. So yeah, but okay, I think the generation should go here, although then it means this is not perfect alignment anymore and it kind of sucks. So you could pass the chunk ref to the storage and say, get me the chunk. But then it's not just a simple pointer anymore. Like just deref the pointer type thing. We could, however, yeah, and then it checks against this one. It's possible to do it that way, right? So let's just build the API for the chunk. You call it map storage or a chunk storage. Let's call it chunk pool. So or maybe the game has the chunk pool and it tells the renderer, hey, here's the chunk pool for you to use. And so they're all pointing to the same thing. I guess who owns it doesn't necessarily matter. And so the map is something which just gets sent. I guess you have a bunch of array of references then. And it's got to be multi-threaded as well, isn't it? It's got to be atomic. So we'll need some sort of a linked list of chunks, like, yeah, it's got to be has it got to be atomic? Yeah, let's make the API. So void graphics render chunk voxel chunk pool init. So pool certain capacity of things, right? The other piece of API you need is like, right, I've got this, like, so one of them is like, I just want to allocate a new one, right? I just want to allocate a new chunk. That's basically it, right? And the other one is like, well, okay, so when you make a new map, that's when you want, that's the only time when you want to allocate. The rest of them is like a copy on write thing. So I think the way to actually say it would be, alloc would be, right, I've got a map, allocate map. Now, because the map will probably go through the chunk pool and allocate them itself. Yeah, maybe you just do it that way. Although it makes the chunk pool API a bit. Yeah, let's say allocate map, because then you can't use the chunk pool API in a bad way, right? So you then talk to the chunk. Oh, okay, no. You never use the chunk pool API directly. You always use, yeah, you always use the map API, and the map does the chunk, use the chunk pool API. Maybe that one's internal. So maybe this pool thing. Yeah. So you can say get chunk. Yeah, no, this makes a lot of sense. So then there's maybe like you could probably call it realloc, or already realloc, because that makes it seem like you want to resize it, but you probably want to call it copy. And you could call it a mutate, but or maybe because the chunk pool API is internal, you just do alloc copy. Yeah. Just make it like this is the low level thing, right? Beautiful. So the sort of the higher level API will be this map one, which is actually used. And so you can say, right, get me a chunk, and that gets you a const pointer, right? So this will say get chunk mute or whatever, and that's to modify it. And yeah. Right, this will work. So we've got to make sure that some of these APIs work across threads. But yeah, I wonder what we could do for... Right, so where does this sort of chunk pool go then? So this internal mapper API needs to be able to access it. And it needs to get initialized. But there is this sort of like GPU in it, and that just calls directly into the graphics VK. It calls directly into there. But maybe what I'm thinking about doing actually is this now takes in some kind of specification, and you're specifically saying like with this chunk pool, hey, how many chunks do you want at most, right? So voxel chunks cap. Right, so it needs to be your map size plus how much you're going to be changing, basically your map capacity plus how many chunks change in a space of in the space of rollback frames count. Then you have like a rollback frames count as well. So it's like a buffer basically of how long they will live on for at most, right? A chunk before it gets actually recycled. So then this system can be completely internal. So that would be equals the voxel chunk pool. And there's just a graphics render thing. It's just the linear array of when it's all turned into linear arrays for the renderer to consume. But we get rid of chunk dim. Right, so get rid of all that and the pool and the API there. So we should be able to take this, go into graphics.c and put this in here and start working on it really. And then we can tidy up yeah, so the beautiful thing is you simply just say chunks, pool chunks equal core allocate me an array please of these guys and capacity. Then the generations as well, you want that. The U16s. Then the capacity is obviously capacity. Now, when you allocate, here's a good question, what do you do? So this is not really correct what we actually need to be doing is, so it's got to be able to be used from multiple threads, probably. Yeah. Let's say it's got to work atomically. So you could start it, you could just have a links list, right? Where all your chunks link to each other and all of this, and there's like a free list. And yeah, you do like a free list, and that's definitely works with atomics really well. And you know, or you could do a bit set, but you've got to scan a bit set. That's the problem. But you might only have like 4,000 of them, so it's not that bad. Um, uh, yeah, not sure. The link list would be easier. Yeah, would probably be better. But then what would you be link listing? Probably just a bunch of entry pointers and stuff like that. So yeah, I think you would do, right, some kind of like atomic down here. Hang on a minute. Align as cache line. Right, so on like a U64, it doesn't really matter at that point, but a U64 for a a bunch of pointers. Yeah, so you probably have a count. So you're bump allocating, and then so that has to be, you can use atomics to look at that one. And then you can use atomics to look at the free list. You have a pointer to a chunk and you just reuse the memory. So you have a free list here. Free list head. And then you can probably have, you need another thing to as well. So that's sort of like, there is that other thing which is called that rollback frames. Right, how many frames of rollback do you have? So this here will probably be a list of chunks that you are going to recycle after the rollback. Yeah, you should have an array of chunk pointers, and it's going to be a queue, actually. Sorry, that can go here. So this would be the queue. We'll call this the rollback queue or whatever. Rollback free queue, something like that. And you'll have the free queue rollback free queue head. And a tail, and you'll just basically every single frame you'll pop on like an empty slot, basically symbolizing that it's reached the end of the queue. You keep popping it until, so the head won't need an atomic, I don't think. I think that's what you'd want. And the tail would need it because the DR lock. So we take that into account. We'll let's work on the alloc code and the dealloc code, and we can change the initialization. So for an allocate, what you want to do is check the count. The atomic load pool count, and you get yourself the good old lock free. So you need to do that sort of while and if atomic compare exchange weak pool count, so the expected value is count, and we want it to change to count plus 1. Now we only want to do this right, so if we manage to do that, then it's a break, and if not, it's going to load, and I guess we can just do the CPU relax thing. Okay, now count plus 1. So you only want to be doing this providing that count is going to be equal to count is less than pool capacity, right? So if we find out the count is equal to pool capacity, what we do is load it from the linked list instead. And then if we fail to do that, that's an out of memory, basically. Now, what are we trying to... I want to double check that atomic compare and exchange in C11, not the silly CPPs. So does it do a load? Performs a load operation. Yeah, good. Just what we wanted to see. So yeah, if this fails, it will basically go back here and load in the new count into there. Job. So here you want to load from the free list head, and it'd be a similar thing. So atomic load address of pool this thing. Now, if this is a valid pointer, so I guess just do a while. Similar thing as this, I think. While p is valid, I want to, change p and set p to, well, that's what I expect p to be if not load it back into there. Then I want to change it to the next pointer. Now, how do I get the next pointer? Well, I'm thinking about storing inside these chunks which have been freed the pointer itself to the next one, because it's a bunch of invalid memory, which doesn't mean anything anymore because it's free. We will recycle it to mean another pointer. So we'll just essentially cast it into a double pointer and then deref it. So basically we just read 8 bytes from that address, and that'll be the pointer to the next. And that should be that. And then that will tick on to the next. Now, if P is still null, then you got yourself big problems. So we just assert the crap out of that. And we just say essentially you've reached that out of memory, basically. So out of memory in the chunk pool, right? We need to up graphics spec voxel chunks cap, basically. Good job. And so this will finally give you a P, right? So P here can be address of pool chunks. Pool chunks count, I guess. Well, it should be uninitialized, but I think that's the wrong way around, actually. I just realized now. I think I want to be doing this one first. First, check the free list. Check the free list. If the pointer is null, then check, then up the count, and your P will be set to this, but then you assert that I think that's the approach you want to take. So now you got yourself a new P. And what we can do is take is 0p basically, so call 0 element deref of p. Or is it just p? Yeah. So 0 the whole chunk, because that'd be nice. Don't give them invalid memory, right? Then return a reference. Now there's a counter element thing involved, right? So these generations, these also need to be atomics. So that's okay. Yeah, we need to atomically load from that. So atomic load from pool generations. And then we need to get the index. So we need to know like what index this is. So it'll just be p take pool chunks, voila. Then that'll be index in there, okay? So you load yourself your generation. Now, with all that being said and done, you can simply construct yourself a reference. Now, this was a pretty cool idea that, I'm glad we remembered this. All of our chunks should actually be aligned to 8K. And this allows us to store in the low bits up to many bits of generations, basically, because the pointers low bits are always going to be 0. And so this means we can simply do this multiplied by size of this. And then we can say, hey, align this to 8K. So these shouldn't be here. Right. But yeah, we're gonna call it like the chunker line. Put it all in the same place, because if not, it's gonna. So you make sure we align it to 8K there. And now, so that means every single chunk is always aligned to 8K, because the whole allocation of all the chunks is aligned to 8K, and each chunk is 8K because it's 16 times 16 times 16 times 2. Beautiful. So here we want to try and guarantee that. So it's best if we put some kind of, probably a static assert somewhere, where we say static assert that that size of graphics render chunk is equal to 8K. And then we say the alignment, so we can say chunk pool chunks are aligned to 8K. So chunk ref graphics render chunk voxel chunk ref can store the generation in the low bits, the MSBs, right? Sorry, the LSBs, least significant bits. Okay. Cool. So now I'm glad we remembered that. We can simply take the pointer P and the generation, slam it in there, and voila. Something like that, right? I probably want to slam some. I think it'll be fine. This is awesome. There we go. So when we deallocate it, we want to make sure that we want to put it on the free list. Now we can probably just chuck it on the head, right? So no, we don't chuck on the free list. We chuck it in the queue. So the queue needs to have some kind of mask. So we'll get that mask at some point, no biggie, but we just yeah, so it's something like atomic fetch add on the pool ref, rollback tail 1. Okay, so I'll get your insert index. Yeah, so you got to get yourself your reference, and we probably want to show we're not doing a double free, basically. So we want to extract out that graphics render generation thing. So that'll just be a ref, get your generation, then you get your index. So you actually want to get your pointer as well. So get yourself a P, and you want to calculate yourself an index, and oh, did we not do that right? Okay. So you get yourself your generation via an atomic load, and you say, right, chorus, so you have like an expected generation. You do a chorus basically generation equal. Now I probably just do this in debug. So a lot of that can be commented out probably. You probably don't need this in debug basically. So you can do something like that. Expected generation. So we can just say, you know, you've passed in, so attempting to, you know, free a past generation, maybe your ticket at this point. Yeah, I think you've got to set a higher bit somewhere. To sort of signify that you might have marked it to be freed, but it's not been completely freed yet. But yeah, this is interesting. We can get this. Attempting to free a chunk basically multiple times, right? Or detected double free of chunk. Okay. Now let's just put it on this thing here. So we say insert index. So it's now pool q insert index and pool mask, wherever that mask is. There we go, equal p. Something like that. So we need a few functions, right? Still, and then we can complete the rest really. So we actually want you to be able to say chunk pool get, right? You take in a reference and you get back a pointer, and that does all that sort of checking stuff. And we also need a sort of an update function, if you will, a sort of like a detected use after free. Cool. So you'll basically return p here. Voila. Amazing. And we need one more, which is like, hey, you have successfully, you know, we're moving on to a new game frame or something like that. So you can say like, yeah, so why should this be inside the graphics system then? Because the game controls this. Right, we can change that in a bit. Let's just write the code out. Let's make the abstraction good. So chunk pool frame in it, you call it. Okay, so it's like, hey, we're doing a new frame in it. And so we just simply, so essentially you want to put on a new element onto the queue. Your first thing is put a new element onto the queue, and you say this is a new frame. Oh, didn't put the mask in the actual place? Silly man. Cool. So you say, right, this is a new key, basically. We'll need to make sure we fill in those as well in the initialization. Yes, this is a new frame, basically, and you want to scan, you want to load the head and keep scanning until you reach either the tail or you reach, no, sorry, you keep scanning until the head until you reach a null, basically. Yeah, so while pull rollback q head index, I guess you could just call it index at this point. Yeah, head index, right. While this is not null, and I guess you can just make that pointer chunk, let's call it P, and you just do sort of brackets. Now, so while this is equal to summon, you then do your property allocation here. Then, so this is maybe like mark for deal. This will better off as mark for deallocation, mark for, and then you effectively in here head index plus equal 1, and then you want to store back in here the head index plus 1, right? Skip over that null. And this needs to make sure you AND it with the mask. Cool. Now, and this is great. So what do we do with these generation counters now? So essentially you need to like tick the generation counter now so that this chunk is no longer accessible. So you want to grab the generation from, grab the generation and probably advance it generation equal generation and, all right, just do it this way. So generation plus equal 1, and then we just do an and equal with the generation mask. So it's that, so it wraps around, yeah? So that's the new overflow, that maximum number. And then you obviously want to store it back. Okay. That is effectively marking it as free now. Oh, and then you want to put it on the actual free list. So there is a free list head. You want to so you take the head. Now you got to be making sure there's no mutation going on here. You got to be ensuring there's no mutation happening. But yeah, effectively you grab the. So I'll put a comment in. Don't usually like comments, but yeah, so you want to grab from the tail or the free list head basically. So you do like your pull free list head next. Hang on a minute. So or you could always just have a tail. Yeah, maybe you can make it a bit more safer just by having a tail. So you say there's always a tail, maybe. And if there's always a tail, then when you allocate, right, let's just do this initialized. So what you would say is instead you'd say my new key will become so you atomic compare and exchange at yeah, so you get the pointer to yeah, while and then you get the sort of chunk pointer. So that'll be you'll find that situated in the tail or something like that. So this is the tail. All free list tail, right? And if there is a tail, I think it's what we want to do. Because you've managed right, then you want to try and atomic store that into there basically, or compare and exchange weak into the next pointer. It's expected to be it's invalid. It's expected to be null. Right, we should do that. So we should null our next pointer. We should null that out. So the one which we're trying to free, we null that next pointer. So now they're guaranteed in the free list to have a null at the end. We expect it to be, let's call it expected. And the value we're trying to replace it with is the P basically, right? And then if this is successful, we can then just atomic store pool free list tail. And we store our P as the new tail. But I'm wondering, like, if they take the head and then they Yeah, you're gonna get some weird thing anyway with this. Yeah, this is... If they take the head and then start freeing it. I think it's just better to just assume with a comment here. Say with a comment, right? No map mutations should be going on. This has to be called at the start of the game frame. And that's where the map mutations will happen. So we can assume this function no mutations, while this function is being called. Okay. Let's just say that. So instead of doing this tail thing, we'll just basically say, right, get the free list head. Just call it head. Now, we make our new one P point to head, whatever it is. And then that should be sufficient, I think. Yeah, that would be better. Right. We're getting very close now. We've got another problem with the generations. Like, this technically doesn't detect a double free. Like, if you free it within the case of the number of rollbacks, then it's gonna... Before it... If you free it after the rollback buffer is done, then sure. But while it's still happening, you can actually put it twice inside this queue, and it's not good. So we want to have a way to sort of mark somehow that it's inside this queue, basically, and going to be freed. And we want to catch that separately. Maybe we do another bit set somewhere, or maybe we just use the generation. We got some bits in the high bits of this generation thing here. We can probably put it there. But yeah. Right, just gonna cool down, and then we'll wrap this code up. BRB. Oh, right, welcome back. Got myself a nice cold drink now. And my laptop back on. Now we good? Okay. Oh, let's finish off this chunk thing. So effectively we're building this little chunk allocation thing which allows it to or pool allocator, which allows us to have some kind of buffer based on the number of rollback frames that there is. So, we don't have rollback frames right now, but I'm pretty sure we're going to be doing it when it comes to networking. And this allows us to just send a bunch of chunk pointers around to the renderer from the game thread, and we know for certain that those chunks will be alive. The renderer is trying to render even if the game is ahead in the future and is trying to change the chunks underneath, because it'll be doing a copy on write type system, which would be super cool. So we're trying to say, like, when you say mark for deallocation, you're going to store in the generations some kind of like bit, right? A special bit. You'll call it the sort of marked for dialog bit. So that will just be, it's a chunk generate. So this bit is going to probably just be the highest bit. Maybe we'll just do an 8, I think, at the end. So you just do something like that will be good enough. And you just simply all that boy on there. So you go atomic fetch or. Just do all in one go. Yeah, so atomic fetch or, so you all that thing on there, and then you get the old value back, and you can just check it there. So this way, when we do the yeah, so we could actually check to see if it has this. Oh, this is so great. If it has this, if the expected generation has it already, then we know yep. Now, something we want to also do as well is when we allocate, when we check the generation, we don't check the generation. Oh no, we never check it there. Right, that makes sense. Right, so in the frame initialize, we should and out this bit. So you and out that bit, add 1, then mask it again, okay? Nice. Cool. Right, so that solved that problem. Yeah, so let's do the initialization code, and I think this is basically done then. So let's go ahead and bring the structure in so we get it all right. We can delete it afterwards, yeah. So The first thing that we want to do is if def this thing. Now the next thing we'd like to do is allocate we want to get the capacity for the rollback free Q cap. So it needs to be a power of 2. So round up right in round up power of 2. In round up power of 2, and you want to do chunk capacity probably +1, because like let me forget. Oh, sorry, let me let me remember, because I think I forget. So right, if it's 1 is a power of 2, right? Or it could be classed as power of 2. So maybe say you do 1. Let's say 2, right? So you did, yeah, okay, so say you did 1. So you did 1. No one worked too well, but say we did 2. Yeah. So you do 1. Sorry. 2 minus 1, and that will be, that'll be 1, and the most significant bit in the index would be 0. You say 0 plus 1, to be 1 shift left 1, and that'll get you 2. So it doesn't, so if it's on a power of 2, it stays on the same one, right? So we do +1, and that means you always have some extra entries in there. Amazing. So you want to basically allocate yourself an array of pointers for the rollback free queue. So that's the rollback free queue. Now the capacity is there. The pull rollback frames count that needs to be passed in. And you'll need to get that from somewhere. Rollback head 0, tail 0. The free list, well, 0 should, it's already initialized to 0. Yeah, let's pass this. Now we need to insert as many as there are rollback frames. We need to insert that into the queue, a bunch of null pointers basically. So you just do null, 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 and that way the code, when there's a frame initialize, will work. It will say, right, keep searching until you find a null, then skip over it, right? So we want to insert that many of those. So it's just something like this. Well, now the mask, that is a good question. Yeah, we completely forgot the mask. So pull rollback mask. That is just capacity, take 1 because it's a power of 2. Amazing. Right, so I think that is everything. That's very cool, man. Such a great idea. So the thing is though, where does this system go? Right, I was thinking it should go in the graphics system, but then really the game like is the one which is going to be calling frame initialize, and if you put in the graphics side of things like a thing to call when you start a game frame, it's a bit weird. So probably not the best place for it, but I don't really want the game really having access to this chunk pool thing to sort of manually be doing stuff. I could create a whole separate system called the Voxel map system. Completely new module Voxel map. You know, it would solve the problem of making stuff isolated, but then it'll be like, you know, the C++ file is going to be like super small, and it's really dumb. When stuff is that small, then you have like tons of modules and files everywhere, and you know, but this is the issue. So this sort of voxel thing, unless I made like a voxel module, right, and it's just for dealing with voxels, and everything voxel related should go in there, and then both the game and the graphics system can use it. And it's not just about the voxel map. That's giving more weight to it being a module now, because you know there is in the graphics Vulkan stuff, right? There's like a voxel model, and like, you know, we do like bit sets of things, and maybe that packing code can all go in there, and then it's, yeah, I think that would be a good thing to do. Let's do that, because then you can make like a GPU shared header and stuff like that. And yeah, I don't usually like doing this, but hey, it's you know, it's convinced me. So let's call it voxel, basically. Voxel module. Get yourself a voxel C. Voxel H. So that's the public header. There's the internal, and then there's the voxel shared header, which would be for GPU basically, and CPU. Now, the best thing is about this is now, right, we don't have to do GFX render as a prefix, it's just voxel. Wow. So that's kind of cool, right? So let's move all this into our new thing. So we'll call it voxel internal. We do a super lovely pragma once, and we do a include voxel.h. Right, so go to voxel.h, graphics.h first. There's this thing called like a voxel map or whatever, right? Yoink. So we'll still keep, we're not gonna like super generic, make it super generic where we go, oh, you can change the dimensions of a chunk, right? Like when we need it, we'll do that. We'll still keep this as an actual specific thing for this game, but it's at least in its own thing now. In a module, so it's reusable for a different game. Which is cool. And also the graphics system is kind of like in the engine code anyway. That's a good point. Right, so we need to include like core.h. Obviously. Okay. So if we go to voxel.c, we can also then go to graphics.c and we can grab this new lovely thing that we've made. Big fan. And we can gradually move bits in here. So this would be voxel internal.h. So let's get rid of all this graphics render stuff. Right, I'm quite happy with that. So that means then so in the voxel internal, you want to have some kind of like voxel system or whatever. I don't know what you're gonna call it, but voxel cache or whatever. And maybe it can do right, so you have this sort of like pool, chunk pool. Now, oh, why has it got this graphics render thing in here? All right, looking good. So that this is an internal thing. Then there will be inside the voxel.c, the sort of cache here. Hopefully more stuff is in there as time goes, we'll see. But for now, this will serve its purpose. Now, inside the public API, you have obviously this voxel map. Now, I think you would just say voxel cache frame in it. So maybe have, graphics.h. Right, I got some more things. These are them. So you have a voxel cache system in the background. And you say voxel init, pass in the spec, and then you have a frame in it, which gets called every frame by the game thread. Okay. And so now we can put a comment here saying warning, right? Must not be called. Warning. Calls to this must not be happening while this function is executing. Okay. Very, very nice. So we just want to take these two lovelies and go into the Voxel C and start doing that. Doing these two. So these are just going to call into the that Voxel chunk pool. In it. So the sort of G voxel cache chunk pool. The capacity is spec chunks capacity. And then spec rollback frames count. Yep. Then the frame initialize is basically the same sort of thing, where it's frame in it. And there you go. So that makes this whole sort of thing internal, and the API is not exposed in any way, which is super, super nice. So there we go. Now, we do want to expose these guys. So how do they work? So this is going to do a get. So we want to be able to do a voxel chunk pool get on, so bg voxel cache chunk pool. The reference is going to be here. And so that will check it. You know, we saw what it did, right? The low bits store the generation counter, but it just basically masks out those low bits and sends back the pointer. And in debug builds, it'll check the generation counter, right? Now, that gets you a constant one. Now, so chunk ref is basically just a pointer with some bits at the bottom being used for something else. So we align the allocations to 8K and we've got 13 bits to be using. So there's a way to get a mutatable chunk, but what this actually does is it says, right, voxel chunk pool, mark for deallocation. So we mark this thing to be deallocated, and it will be deallocated after the many rollback frames have been ticked, basically. And then we want to mark in this guy. So I guess we can get the pointer. We call it P, I guess. So we just say P. So yes, it's the pointer to the reference. So deref P. So mark for deallocation that reference, please. Thank you. And then we want to deref P again and store in there a new sort of like voxel chunk pool alloc. And what you really want to do is completely clone it, right? So I guess you can sort it. Right, we've got a few things to be doing. We want a ref pointer. So So cache chunk pool, but maybe we'll care about is the chunk pool. Right, what was we doing? So I was going to allocate something new. Let's just be on new chunk ref. Yeah, this would be the new ref. Now we want to get the new P and the old P. The new P is just voxel chunk will get. It's kind of a bit silly, it checks the generation, but it's only for debug builds, right? So might as well. So new ref, new P. Now we need the original P. So we can call it source P and destination P. So that'll be a simple copy element. Wait. Copy element is simple. It's just dereferencing. Right, literally just a complete clone of the thing. Because it's just an array. Lovely. So clone it. Hang on. Then this one is equal to the new reference, a new ref. And you return the pointer to the destination P. So now this one is mutatable. Yeah, this one's now mutatable. It's just... Yeah, so I guess if you mutate many times in a frame, then it can become a problem, but we can change the API if we need to. But yes, this doesn't make any sense. So we get the pool, right? We get the chunk, the reference pointer thing. We deallocate, we mark if deallocation, and then we allocate a new one. We get the source pointer and the destination pointer, and then we copy and we store it in the map as the new one. And voila. Amazing. Cool. Right, so let's just double check. So mark for deallocation is gonna... Yeah, let's double check the code. So initialize, run that power of 2 the capacity. Yep. Yep, that makes sense. So the chunks needs to just allocate the bytes manually with a special alignment of 8K. The rollback free queue needs to just allocate a bunch of chunk pointers. And they're the pointers to the ones which we're gonna free. And that's the queue worth of those. Capacity, all the rollback frames count. And the mask is one take the queue because it's capacity because it's already a power of 2. Then we append to the insert, append to the tail the number of frames and just put a bunch of nulls in there to mark the end of that frame. Now frame initialize called every frame is going to get the head. Keep advance in the head. So while the P is equal to something, we keep scanning over, checking the generation by removing the deallocation bit and adding 1 to the generation, masking it back in and storing it back. And then grabbing storing the next pointer in the free list. Sorry, making the item we're about to free by storing in the first 8 bytes of what's at the chunk. Rather than storing chunk information, we'll just store a pointer in there, and that's where the free list head used to be, and then the free list head now becomes the P. Then we add 1, keep going around until we've actually freed all those elements now, and now they're available when we next allocate. And then we store the rollback requeue head, which is head plus 1, which skips past the null entry. Then we store a null in there again to mark this is a new frame. Cool. But yeah, we shouldn't be calling any mutes. Yeah, that's good, that's good, that's good. So get is just gonna get the pointer by masking out the low bits, get the generation by masking the new bits and keeping them. And then yeah, get the generation counter, detect. Yeah, so this is where you need to mask out the deallocation bit, because otherwise it's not going to be equal. Right, I'm glad we caught that. So even if it's been marked for free, we're still able to get it for so many frames, right? That's the point. Because the game logic thread is going to be ahead. The next frame's game simulation is going to be ahead, and the thing which is currently rendering is going to be behind. Right, we're probably doing rollbacks, so probably be some kind of... We're keeping the chunks around for as many as we can roll back to, basically, right? So that's all very good there. So allocators can get the free list head, atomic load. So this can happen across many threads if need be. While this pointer is equal to something, we get the next chunk pointer that is pointing to. Yeah, if it's equal to null, then that's fine. Cool. Yeah, that's good, that's good. Get the next one that it was pointing to, and compare and exchange weak. If you manage to compare and exchange, then break, and you're trying to put the next pointer in there, and if not, it will load the next one into P and then carry on. Now, P is either equal to null or something. If it's equal to null, we just bump allocate the count up. So we don't have to pre-populate a list. We just bump allocate. Then well, we could, if we pre-allocate it would technically be better, because well, you have to go over all the entries when you initialize, that's the downside, but when you're running, it's even quicker, because this branch won't exist anymore. But yeah, there's that. Anywho, just bumps, does the same sort of thing. Yep. 0 is the data, that's what you want, and then loads the generation counter in there, and voila. Deallocation, get the pointer, if we're in debug, fetch, then or, atomically this mark for deallocation bit on the generations. If it already has it, then we've tried to free it twice. If the generation is different, we've also tried to free it. Free an old one, basically. And then we add that onto the list to be. Cool. That code looks good to me. Don't see any issues there. Amazing. So, this means now we just gotta so no longer is there a voxel chunk update. We instead actually want to just send the whole map in there now. So let's just get rid of this. There's no longer any chunk updates. Very nice. And then game side as well, same thing. So I'll leave this in for next time so I remember. Like, to do. We want to send the whole, right, voxel map structure now. Now I'm considering actually that voxel map, right? What happens if this is just this? Is that the flexible array member? Yeah, exactly. That's what you want. Hey, yeah. Yeah, it's a little bit confusing. I'll explain what it does. Drawing time. And how's it going? It's a long time no see. So imagine if, right, it's a pool allocator. Each one of these is a chunk. Each one of these is a chunk, a voxel chunk. Okay. And it stores 4,096 voxels. Now, initially we allocate this one. We allocate this one. And then, excuse me. And we allocate this one. Now we decide to free this one. So now this, well, okay, let's say we keep allocating all of them. Right, say they're all allocated, let's say that. Say we want to free this one here. Well, what we're going to do is we're going to set this as the free list head. Now this is the free list head. And we're going to store at the first 8 bytes in here a pointer to the next free list head. But because there's no because there's nothing freed yet and there's nothing in the free list head pointer, it's just going to put a null in there, right? So that's a null. So we'll put n in there for null, yeah? So now the next one that we free is this one over here. Oh, let's say this one here. So now it's going to write into the first 8 bytes of that memory region a pointer to the next free element. Ta-da. And then this element is now the free list head, right? So then say we free this element, this chunk. Now we write into the first 8 bits so 8 bytes. And now this points to the current free list head, which is over here. And this now becomes the free list head, right? And so on and so forth. So what we're doing when we're doing this whole sort of like chunk double pointer thing, right, is we're saying, hey, grab me a chunk pointer. So you got a chunk, right? It's just a bunch of memory, right? U16 times 16 times 16 times 16. It's quite big. It's 8K KB. When we're doing this, we're saying, I don't care that it's a voxel chunk, right? Like, get me. I'm gonna pretend that it's actually just a pointer to a pointer. So we're just gonna pretend instead that it's actually something like this. You see now, so it can either be a pointer if it's freed and nothing is technically using it, but if it's being used and it's allocated, it's actually just an array of voxels. So that's what that cast is doing. Is it's just reusing that memory to store a pointer in there for the free list. Does that make sense? So when we want to fish it out, we get the free list head, we load the pointer to it, and we get the next pointer that it was pointing to, and we say, right, replace the free list head with the next pointer, and now this is mine. Right. Yeah, what would be pretty cool is if we do flexible array member. Now that would be great, because then you can literally just like copy the whole thing by, like, we can literally just make this be cool. So you can do like so you got to do a thing like, right, allocate, we can call it allocate flexi, maybe. I need a new one. Well, yeah, allocate array. So you want to do a T. It would be cool if we did this automatically. Let's call it allocate flexible array, okay? So imagine if we could do something like, maybe you don't need T. Do you need T? I think you need T. You need T. It kind of sucks, but anyway. So you have the header and you have the array. Size of header plus array size of header, something like that. So all you're doing, hang on a minute. Yeah, I think you want to pass in an allocator actually, because I remember the payload has a way to make itself into an allocator interface. So that is like super cool. Yeah, so I think we'll do that. So you do something like come on. Oh, whoops. Yeah, so we want to nulls basically. We could spin over the pool and allocate all those. But yeah, that's an interesting point. Like, if the ref is 0, right? So you get the ref. If ref That's better. So now it works for null. What were we saying? So like if it's got a reference in there. Good, good, good. Okay. I'm happy with that. Yeah. So we probably want to have a function where you can like clone it. You can copy. To make a deep copy. Or just call it clone because it's probably quite. Nah, copy. DST source. So you're not actually copying the whole map. You're copying. You're literally just copying the. You're copying chunk pointers. Oh, nice. So call copy element many. Destination is DST chunks. Source chunks. And the number of elements is the product of source dims. Hey there, Ripple HKG. Hello, stop solving your British. Cup of water. Solving? What do you mean? It's my glass of water. You know, it's my glass of water, mate. Not sure what you're saying. But yeah, so now we've got copy functions. So essentially, in the payload, man, this would be so cool. Man, this is such a good solution. This is great. Now the payload doesn't get a massive amount of data; it just gets what it needs. The renderer doesn't have to have its own separate copy, neither does the game thread. There's one copy that sits globally somewhere outside of the game and the renderer, but the chunks are kind of copy on write, and the chunks will eventually be recycled when enough frames have gone. So that way the renderer can read from the past and the game can mutate into the future. There we go. That's going to be awesome. So we want to send the whole map structure now in the graphics payload. Now we scream the start here next time. And just in case it wasn't obvious enough, we just... There we go. Do I dance? No. I'm too tall. Too tall. I don't know where my arms go. My arms either end up in someone's face or by my side for too long, so the answer is no. But yeah. So we've got some slight sad news, guys. I will not be streaming this Thursday or this Friday, which the stream schedule usually says. You can keep up to date on, you know, when the next streams are, what we're doing in the next stream. I posted a little thing in the announcements channel in the Discord. You can come and ask more questions over there. But you know, I got some. Basically, I'll just be out of the house for Thursday, Friday, so unfortunately I can't do that. But I might do a surprise stream on Monday, right? Obviously not a surprise for you guys, but I might do one because I've got Monday off work now. So usually I have Fridays off work, but I got Monday off work this time around. But yeah. So there is also a YouTube channel if you want to go and look at the, you know, if you're interested in what game we're making or the direction of the project is, you can go and find more about that on the YouTube channel. And if you want to support the stream and get access to the code to run your own local machine, you can support the studio over at Ko-Fi. And thank you for everyone who's supporting the channel already. I really appreciate you guys. But yeah, next stream, essentially, we're going to be getting the renderer using this sort of being given this map. So the game making a very simple map, like we've already seen on the screen anyway. Make that initialization time, just do some generation. The renderer then has the new map already, and we want it to emit graphics render voxel model instances on the render thread. Right, so we're not having to fill the payload up with loads of stuff it doesn't need. Or maybe there's a callback that can happen which allows the game to do this. We need to figure out which way that is, but it's something like that. Yeah, we'll figure that one out. I might do the callback method, I'm not sure yet. But yeah, stuff to figure out. And then once all this stuff is in, we can then, we have our map representation, then we can start doing procedural map generation of, a quite big map, a 1 kilometer by 1 kilometer, where each meter has 16 voxels in it. So it's quite, it's quite a lot of voxels in a map, right? The detail is quite crazy. So you'd be able to, you know, it'd be 16K, right? So yeah, 4. Right, that's just across the flat plane. Um, across one plane, that's like 256 million. But yeah, you easily do 64 times 16, whatever that is. So there's quite a lot of voxels, basically, is what I'm saying. And it's gonna be fun. So we're gonna try and be getting this working. But yeah, in the meantime, guys, hope you have a good one. The next stream will be next Sunday. So I'll see you all there, hopefully. And if not, I'll see you guys in the Discord in the meantime. Right. God bless you all. Have a good one. Much love. Bye bye.